Hello everyone, welcome to the control system. This is lecture 10 on the hand waving introduction to PID control. This is the outline of these lectures, okay? And you can find the study material from this link. Okay, so let's begin with the introductions. And this is a block diagram of the closed loop system. And the role of the closed loop system is to keep the measure output from here to a predefined value, which is a set point, the target value, or the desired value. Okay? The same name. So in electrical system, the physical signal can be voltage, current, powers. For mechanical systems, it can be position, speed, force, or torque. If you consider a hydraulic system, it can be the pressure, the flow, and so on. And the difference between the measurement output and the set point is called the errors here. Okay? And this error will be sent to the controller. The controller do some computation and it generate control output, which is the actuation signal. Okay? And this sent to the plant via the actuators, and then the plant or the process will produce the output, something that you want to control. Okay, and of course there is a disturbance going to the system, and the job of the control engineer is to design this controller. Okay, so that the signal Y should follow this set point or the reference. And in this lecture, we'll focus on PID control, which is widely used in industrial process. Okay, and PID control is everywhere. It has been extensively used in process control. For example, in this industrial plants, you want to control the flow of the liquid in the tanks. You want to control the temperatures in the tank, the pressures, and so on. In robotic, for example, in this robot arm, you may want to control the end effector of this robot to follow some path or some trajectory. It can also be used to control the drone. In fact, just the proportional and derivative is more than enough to control the drone with some limitation, but yes, it is possible. And much more, because it's everywhere, the PID control. And by the end of these lectures, you will be able to use on-off control and PID control. And the important part is know the way to tune the parameters in the controller effectively. And this is the full PID control. Sometimes it is written like this and sometimes it's written like this, but both of them are identical. And you don't need to worry about the math here right now, so we'll go to the detail later. Okay, so let's move to the on-off control. Okay. For simplicity, let's consider how to control the temperature in the oven. So the temperature in the oven, this is the oven, and it has the sensors. Okay, so the sensor will measure the temperatures and fed it back to the controller. In this case, for simplicity, the switch is a controller, and based on the difference between the set point temperatures and the measured temperatures, the heater element are turned on and off by the controllers. Okay, this is a simple on and off, just switch on and switch off. And if you draw it in a schematic, in a block diagram, you can draw it like this. Okay, this is the schematic, show the block diagram for controlling the oven. So this is the oven, And you can identify the following elements. There is a controller, which is a switch, a plan here, which is an oven, and this is the feedback. Okay. And the goal of this controller is to make sure that this Y, okay, reach this target set point or reference value. For example, if over 20, the controller will do some calculation so that it reach 120 degrees. In this case, very simple, just on-off control. And U here is just heating effects. You can limit it from 0 to 1, and actually you can scale it up to higher value, let's say 0.0 watt and 1 for 1000 watt. This is the control input. We'll go to the oven. Okay. So the industrial oven have two important characteristics which need to be explained because they affect the response of the controllers. One is called the dead time, and another one is called the capacitance. And in practice, the system cannot respond immediately, and it takes some time until the controller output has any effect on the measurement output. Okay, so this is called dead time. This one, tau is a dead time. It's the delay in the system. In case of industrial oven, if the access door is open, it takes time until the temperature drop, and the controllers send the different turn the heaters on, and the temperature will brought back to the set point. Okay. Another important property is the capacitance. So the capacitance of the system is seen as the resistance to the changing input. I'm not talking about resistor or capacitor in electrical circuit. Okay, it's a capacitance of the system is seen as the resistance to the changing of the input. The higher the capacitance of the system, the longer the time it takes to react to changes. Okay, with the cold ovens, even if turning the heater on, then it takes for the temperature to start increasing and reach the nominal value. And in control theory of the system, in the theory of control of the system, the industrial oven is defined by the first order process with dead time given like this. This is the dead time and this is the capacitance. Okay, and this is the on-off control. Very simple. This is the simplest possible controller ever invented. So in this case, if the error is larger than 0, it means that YR, the reference larger than the desired, no, the reference is larger than the measurement output. The controller will output this Umax. Okay, if the error is less than 0, and it will output the Umin, just the minimum value and maximum value. And there is no intermediate point. It's just on and off. Okay, and this is the schematic. So if the error is larger than 0, it will switch to on, maximum value 1 in this case. If the error is less than 0, will switch to off, which is 0 in this case. In the case of the on-off control for the oven. Okay. And this is the schematic block in the Simulink. You can find the source code in the GitHub. I've already uploaded. So in this case, it has the oven. This is to mimic the behavior of the real system. It's very simplified version of the oven. Okay, and we have the transport delay block in the Simulink. This is for the delay, and then the signal is then fed back to this junction. It compared between the reference value, in this case 120 degree, and then send it to the on-off control. in this case it's just a switch. So uh, if the signal is larger than 0, we'll switch to 1, and if it's less than 0, it will switch to 0, and then it's sent to the plant. Okay. And this is the result if you run the simulations. So in this case, I start from 0 initial condition, which is a default value. You can add the IC block to set the initial conditions after delay and set it to the room temperature if you want. So here is the below here is the control signal, which is the output of the controller block, and this one is this signal is a reference signal, and the blue one is the actual signal. Okay, and from this plot you can see that there is a delay for 30 seconds because we added a 30 second as the delay, and the signal start to increase. So at this case, it start to increase because the target value is 120 degree. So at this point, the error is what? Is less than 0, right? This is the actual and this is the reference. So when the error is less than 0, the controller switches to 1. So that's why you have this signal 1 here. Okay? And at this point, it reached the target value. But but the oven is still hot, and the heater keeps heating up, so that the signal is about the reference. When the signal about the reference, the controller will switch to 0. And then when it reached this point, it's reached the reference, but the oven is cooling down. It cannot stop immediately. So the error is, when the signal comes here, the error is less than 0 again. And the controller switch to 1 again. And this process repeats and resulting in these kinds of oscillatory behaviors. For some application, this kinds of behavior is acceptable, especially if this magnitude is very low, around the desired value, around the reference. Consider the heater in your house, for example. It might be okay to have the temperature just around here. But for some applications, you don't want this kind of behavior to happen, especially for something that can move. For example, consider the cruise control that we discussed in the first lectures. You don't want its velocity to be oscillate like this. Okay, it will be very uncomfortable, and the actuator won't last very long. And in case of the drone, for example, you don't want this the control signal to be on off. Like first you need to generate the thrust to the maximum, and then you set the thrust to the minimum. So there will be a disaster in the case of the drone. So it will result in wear on actuator and oscillation behaviors. But it also works for the simple dynamical system with low performance requirement, the heater, for example. So as you can see from the previous example,